Section 2.1, Frequency Distributions and Their Graphs. Frequency distributions are a method of looking at data in a graphical format. Often it's much easier to see if there is a pattern or some type of calculation that's readily seen graphically that's very difficult to look at by just seeing a list of information. For example, I have a list here of the age range of people who exercise at least 3 times per week, from ages 10 to 20, 21 to 30, 31 to 40, all the way to age 80 in 10-year increments. And then to those increments, I have the number of individuals exercising from this total group. It's a sample. And I can see some patterns here on the left, but when I see it represented graphically, and this is a tabular distribution on the right, with the age ranges on the bottom and number of individuals who exercise that at least 3 times a week on the left, I can clearly see a pattern that as we go up from ages 31 to 40, that's the highest. 41 to 50 is the second highest. It seems to ascend and then descend after a while. We'd have to explore further why there's more people in the middle ages age range exercising. Could be have to do with health. Could be have to do they have kids and they feel they should live longer, or maybe they're gaining more weight. But we can't make a judgment on that. But we can clearly see a pattern telling us we should explore further. Now, when we do a distribution in terms of frequency, there are several things we have to look at regardless of what we are analyzing. This is the same graph. And what we have here are how to set up the graph when you have the data. First, I want to understand we have a lower class limit and an upper class limit. I've got some arrows pointing here. This is the range. On this middle graph, this middle bar, we have the lower class limit, the lower, which is 31, age 31, and the upper class limit is 40. So whatever age someone falls in, they're going to fall between 31 and 40. If they're age 30.5, we would probably put them at 30. If they're 31.2, they go between the 31 and 40. So we later determine how we distribute this. But at this point, I just want to understand that is that range within each bar, the lower class limit and the upper class limit. There's the class width. And the class width is the difference from the lowest to the highest. And then the frequency is the number of individuals in this case by the age range that are exercising. That is the raw number within each category. Now, I've got another set of data here, even more difficult to see a range here and what's going on. But suppose we want to make a frequency distribution, and this is a step-by-step. This is also in my Microsoft Word notes as well. I've got age examples here from ages 12, and I put in order here, all the way to 65. And this is the age of someone the first time they get prescribed glasses. And how do we develop this? We could have unlimited numbers of bars for the lower and upper limits. But to understand this with the human brain, we really want to look at only a certain number. And I put here in bolded, we want at least 6 categories. If we want 6 categories, the class interval will be 9. I'm going to show you how we get to that. Now, in this case, I've sorted this from lowest to highest, and I will in any quizzes or tests as well. I don't want you spending time manually sorting. My lowest is 12, my highest is 65. So my ultimate range is 65 minus 12, which is 53. So from age 12 to age 65, that is 53 years. Now, if I want 6 categories, and I'll tell you why the number of categories we will have determined in a moment. If we have 6 categories, I divide 53, that range, divide by 6, which is 8.83. Now we have to have whole numbers categories. So I'm going to round up to 9. So if we know we want 6 categories, the class interval will be 9 for each class. Now, why did I pick 6? Well, if we have too few groups, if I distributed the age range for the first time someone got prescription glasses, if I just had 2 groups, ages 10 to 40 and age 50 to 80, it's hard to see. There'll be more people in 10 to 40 than 50 to 80. Yeah, you can see not much of a pattern here. If I have too many categories, where I've got a differences of 2 between each age, very difficult also to see something. Now, with the human brain, we'd like to have at least 4 categories to see if there is a pattern, but no more than 10. I decided on 6, and we could have done 8 or 7 or 5, but we'll go with 6 just for example's sake. But anywhere between 4 and 10. Less than 4, difficult to see if there's a pattern. More than 10, it's very difficult to encompass overall for a strategic review of this. Now, as I said, we picked 6 categories, and that width was 8.83, but we rounded up to 9. So now we're going to develop the classes. We don't have to start at the lowest number for the lower class limit, which is 12 in this case. But that lower class limit must be within the first class. I could start at 10. As long as that lower class, the lowest one is in there, that 12, that's fine. But in this case, I'm going to go I'll start at 12. Now, I want you to notice something here. 12 to 20, because that 12 to 20, it sounds like 8. But when we're counting the number of individual units, it's actually 9. And that is our category width. Why? 12, 13, 14, 15, 16, 17, 18, 19, 20. Why 20 minus 12 is 8, we actually have 9 individual ages here. So it's 9 separate units. The rule of thumb is this. Subtract the highest from the lowest, add 1. 20 minus 12 is 8, plus 1 equals 9. So I'm going to do this. 12 to 20, that's my 9, first 9. 21 to 29, 29 minus 21 is 8, plus 1 is 9. 30 to 38, 38 minus 30 is 8, plus 1 is 9. So I'm showing you we have 9 separate units, and that is our class width. 39 to 47, 48 to 56, 57 to 65. Those are our intervals. Those are going to be at the bottom of our bar chart. Now, what I'm going to do here is I'm going to count the number of units within each range. My 12 to 20. Lowest is 12, the highest would be 20. Well, I made these bolded in yellow, this first one. 1, 2, 3, 4, 5, 6, 7, 8. There's 8. 8 I've highlighted are between age of 12 and 20. So the frequency to 12 and 20 is 8. And I've done this with all these. There are 6 in the green from 21 to 29. There are also 6 in the light blue from 31 to 36, which is the category 30 to 38. In the category 39 to 47, there's also 6. There's a bunch of 40s and a 42, but they all fall between 39 and 47. 48 to 56 have 2, and I've color-coded these so you can follow. And then 57 to 65, there's also 2. I'm looking at the number within each category, and that's what I've done here. We've got 6 different categories. We've got separated by 9 within each category, and then I've counted the number of unique components within each one of these class intervals. Now, from the previous page, what I've done here is I've brought that table over I've developed by the different age groups with the frequency by age between 12 and 20, 21 and 29, as we developed, that someone gets glasses for the first time. As we said before, 8 people between the ages of 12 and 20 in the sample get glasses for the prescription glasses for the first time between the age of 12 and 20, and so on and so forth. And I developed this graph. I've also color coded it for you to see. I wouldn't normally do this, but I wanted us to understand what we're doing here. So at 20, there's 8. My bar is 8. All the way from 57 to 65, there's 2 people within that age range, and that's why I've got 2 on there. Now, relative frequency is based on the percentage. The graph will visually look the same, but instead of looking at by each age range, 12 to 20, 21 to 29, I'm looking at the percentage, and I'm looking at the total. There are 30 individuals within this sample. Again, 12 to 20, there's 8. 21 to 29, there's 6 individuals. 30 to 38, there's 6. The total is 30. Now, the fraction of the total, I've got 8 out of 30 in the age ranges 12 to 20. I've got 6 out of 38, 21 to 29. That fraction, when I divide it, shows me the percentage. 26.67% are between the ages of 12 and 20. That's the same as 8 out of 30. But with the relative frequency, we make it out of a total percentage. 6 out of 30 is 20%. 2 out of 30 is 6.67%. And when I add all these up by the individual categories, I get 100%. Now, what you're going to see here, as I said on the next slide, the graphs look the same visually, but instead of raw numbers, we're looking at percentages. And there's reasons we do this, depending on what story you're trying to tell. As you can see, this is the same visually as the other one, except I've only got percentages here. That's the difference. Same categories, and the relative difference between them visually, you can see they look the same as raw numbers. But a lot of times, raw numbers may have no meaning, but when you have a percentage, you can get a relative scale when you're trying to tell a story of what is going on. Now, the cumulative frequency is based upon the same data, but we keep adding the previous component to it. And what this lets us know is where the trend is going as we get larger and larger areas put together. For example, I've still got the same class intervals, 12 to 20, frequency is 8. So the cumulative frequency for that first component is 8. And the percentage would be 26.67% as before. But then we add 6 in the 21 29 to that 8. 8 plus 6 is 14. 14 out of 30 is 46.67%. We go to 30 38. We add the 6 to that 14, which is 20. 20 out of 30 is 66.67%. This shows us how quickly something builds up. Is there some kind of exponential, logarithmic, algebraic pattern to this? We're just observing, but we're seeing if there's some kind of trend we should be exploring further and why that trend is going on. When I graph this, again, it looks like this. The 12 to 20 for the cumulative frequency is 8, then 8 plus 6, that's the 14. You can see how this builds up until we get to all 30 on the final class, which is 100%. Again, these are the numbers. This is a cumulative frequency. This is a cumulative relative frequency with the percentages, as we showed before on 2 slides, where it goes up to 100%. As you can see, these patterns look the same, but sometimes it's easier to understand a percentage rather than a raw number, especially when you're trying to explain or tell a new story. We can also find the average of all of them. Between 12 and 20, the average would be about 7.5. This is called an ogive. An ogive graph is cumulative and it adds the midpoint of each class frequency to the cumulative frequency. Again, we're looking for a pure pattern here. And as you can see, in this case, for example, the age people that got eyeglasses, it seems to build up consistently to about from 12 to 47, but then drops down quite a bit. We also look at a modified ogive called a concentration curve, where we look at the accumulation of all the information until it gets to 100%. This is powerful. You can see where something is concentrated. What I've got here is an example of the number of doctors prescribing a certain product. Could be, for example, anti-inflammatories, one of the most common prescriptions there is. And I've got 256,000 doctors in the United States that are prescribing anti-inflammatories. My top 10% of doctors, and that's by prescription, I have 1,000 doctors in the top 10%. You can see on the third column from the left, cumulative number of prescribers within each percentage. And that percentage is the average number of prescriptions per doctor. So in other words, 1,000 doctors do 2,000 prescriptions a year each. If I multiply 1,000 doctors times 2,000 prescriptions per doctor, that's 2 million. The next 10% would be I have 3,000 doctors. I'm sorry, 2,000 doctors doing 1,000 prescriptions each. Instead of the top 10% where it's 1,000 doing 2,000 each, I got 2,000 doctors doing 1,000 prescriptions each. Again, that is also 2 million. Each one is broken up by the 2 million increments. So in other words, among by 10% increments, there's 20 million prescriptions out there. How are they distributed within the top 10% prescribing each by these 256,000 doctors? From 20 to 30% is 4,000 doctors, each one doing 500 prescriptions each annually. And again, that's 2 million. Each one of these is 2 million. I'm sorting it from the highest to lowest doctor. And at top 10%, where there's 1,000 doctors, each does an average of 2,000 prescriptions, where it's 2 million. By the time I get to the bottom 10%, from 90 to 100%, there'd be 100,000 doctors doing an average of 20 prescriptions a year. That's still 2 million. But you can see there's a lot more doctors doing less prescribing in that bottom part than there are. Each one's doing a total of 2 million prescriptions. But how many are they doing individually? That's the total prescriptions in each class. Each one's 2 million. When I add that up, I'm going to look at two numbers here. The cumulative amount, 2 million for the first 10%. From the top 10% to 20%, add another 2 million. That's 4 million. You can see I keep adding 2 million for each 10% until it gets the total amount, 20 million. Now, where this is interesting is when I graph this. 1,000 do 2 million, 2,000 do 4 million in total. So from 78%, 70,000 do 16 million. From 1,000 to 70,000 do 16 million in total. Let's graph this. And I'm going to explain this graph. On the x-axis, our horizontal axis, we've got the number of prescribers of this anti-inflammatory. There are, like I said, 256,000 doctors in total. On the left here, on the y-axis, the vertical axis, I've got what percentage they make up. Now it's cumulative. And when I look at this, is you can see 50% of all the prescriptions, which is 20 million prescriptions, is done by only 12,000 doctors. I've got 256,000 doctors in total prescribing, but 12,000 of them do half all the prescribing, do 50%. And if you want to go even further, it looks like about 60% is 60% of all the prescribing, and that's 60% of the 20 million is done by about 50,000 doctors. This is a concentration curve. This tells us where all the concentration is of who's doing what. It's where the old 80-20 rule comes from, where 80% of all the purchases are done by 20% of the people. Well, it looks like 50% of all the prescribing is only done by about 5% of the doctors. Pretty powerful. So if I'm a pharmaceutical company, there may be 256,000 doctors out there, but most of my business comes from only about 12,000, and that's what I'm going to concentrate on. Hence the name concentration curve.